Hi, everyone. This is going to be Unit 2 Notes Part 1. And Unit 2 is going to be all about molecular and ionic compound structure and properties. So getting started, we're going to talk about specifically bonding. To define a chemical bond, if you've forgotten what it is, it's forces that hold groups of atoms together and make them function as a unit. So basically, when two atoms bond together, they are going to be held together by a force that essentially forces those two things to act as a singular unit. So why would that happen? Why would two atoms want to be bonded together? Well, bonding lowers the potential energy between positive and negative particles. So if something's going to lower potential energy, that's going to be a more stable state, because as we learned in regular chem, high energy states are more unstable and lower energy states are more stable. So to define bond energy, that is going to be the energy required to break a chemical bond. And we express that as delta H in kilojoules per mole. Bond length is going to be the distance between atoms where the energy is at a minimum. So bonds can stretch a little bit. So we consider a bond length to be when that energy is at its lowest or its most relaxed state, and that's how we measure our bond length. If you have a higher bond order, that's going to result in a shorter bond length and a higher bond energy. And by bond order, I'm talking about double bonds, triple bonds, single bonds. If you have a higher order, like a double or a triple bond, that's going to be a shorter bond length. Okay. So you should already know the different types of chemical bonds: ionic bonds, covalent bonds, metallic bonds. But if you're not sure, you don't remember, here's a slide that'll tell you. We have ionic bonds coming up first, and those are electrostatic attractions between oppositely charged particles. So usually metals with nonmetals, anions with cations. An ionic compound is going to result when a cation or a metal reacts with an anion or a nonmetal. The nonmetal is going to be so electronegative that it's going to steal the electrons from that metal. So as you're seeing in this diagram down here on the right, we have atom number 1, the metal, which is not electronegative very much, as the much higher electronegative atom number 2, which is our nonmetal. And so that electron, the red one here, is going to be transferred right over to the other atom. Now that forms an association between the two of them. And now it's a weak association because that electron is going to hang out with the nonmetal. It's not really going to hang out with the metal at all. So if you were to dump an ionic substance in water, which is polar, it would just yank those two pieces right apart and the thing would dissolve immediately. Because again, ionic bonds are fairly weak. Okay. Covalent bonds, on the other hand, are a much stronger bond than an ionic bond. And that's because instead of an electron transfer, we're seeing an electron share taking place. So over in these diagrams over here, you're seeing some of that represented. You could have an equal share, which is a pure covalent bond, as you're seeing represented here between these two chlorine atoms, or you could have a polar covalent bond, as you see represented by this hydrochloric acid molecule over in the right-hand corner. Pure covalents take place when electrons are shared perfectly equally between two atoms. So that generally is only going to be a true pure covalent bond between atoms of the same element. No two elements have the exact same amount of electronegativity, right? But you can get pretty close with atoms that have very similar electronegativities. Polar covalent bonds, again, are going to take place with two atoms that are fairly electronegative, but there's a difference between them, okay? So an example of a polar covalent down here would be hydrogen and fluorine. When they bond together, they become hydrofluoric acid, but the bond looks like this, H bonded to F, right? But fluorine is much more electronegative. So we would put this little delta negative symbol next to the more electronegative atom, and we're going to put that little delta positive symbol next to the less electronegative atom. So to draw it a little bit more clearly, it looks kind of like this and like that, okay? We can also use a notation that looks like an arrow here to represent dipole moments. Same situation. Your arrow is going to point towards your more electronegative atom, and that little cross is going to go next to the less electronegative atom. Okay. So just to be a little bit more specific about electronegativity notation, that little funny looking S is the lowercase Greek letter for delta, and that is used to indicate a fractional or partial charge. We don't just call it positive or negative because it's not a true charge. That molecule, HCl, is neutral, but it has a partial positive charge on one end and a partial negative charge on the other. And that partial negative is going to exist next to our more electronegative atom versus our partial positive existing next to the less electronegative atom. Okay. The arrow, again, that's representative of what we call a dipole moment and points toward the more electronegative atom. So dipole moments, when you have a molecule that is polar, that partial negative charge and that partial positive charge creates two different poles on our atom. So to represent that moment, that's what that arrow means. So this notation, the little funny looking S's versus the arrows, they mean two different things, though those two different things are very closely related. So if I wanted you to label electronegativity, you would use this notation. And if I wanted you to label a dipole moment, you would use that notation. Okay. Metallic bonds, we're not going to spend a whole lot of time on metallic bonds in this class, but basically metals are special. They don't act like everything else when they bond with one another. They're actually going to pool their valence electrons into what we call an electron sea, and they can flow and move freely between each metal ion core. So you're seeing that here in this diagram on the bottom right. You're seeing all these delocalized electrons, and they could just cruise around and move any which way between everything. And that is going to cause some really cool properties, right? So malleability, ductility, that happens because of this free movement of electrons giving metals different properties. It's also what causes them to be able to conduct electricity as well as they do. Down here, I just put a diagram of an alloy really quickly, because when different metals are bonding together and associating with one another, you get what is called an alloy. And that's just a mix of different metals together. So bronze would be a good example of an alloy. Real quickly, let's go over bond order one more time. It's a really easy concept. First order bonds are single bonds, second order bonds are double bonds, and third order bonds are triple bonds. So if I were to ask you to analyze a molecule for me, you would go and look for all the triple bonds and you'd call those out as third order bonds. You look for all the double bonds and you'd call those out as second order bonds. And you look for all the single bonds and you'd call those out as first order bonds. Where that gets a little bit dicey is when you have something called resonance, which we'll talk about. And that's when you have some delocalized electrons kind of moving and hopping from one place to the other. So our double bonds or whatever can move around a little bit. So in that case, you would get a bond order of 1.5 or something like that, which would basically just indicate that sometimes that bond is going to be a single bond, sometimes that bond is a double bond, but realistically, those electrons are moving around. So this is one of my favorite graphics, or type of graphics, I should say. It's a little bit blurry, but it really shows you in 3D the different levels of electronegativity. So if you're looking at this and you want to know what kind of bond is going to take place between nitrogen and oxygen, well, those have really, really close electronegativity. So more than likely it would be a covalent bond. But if you were talking about fluorine and potassium, that's a huge difference. So that bond is more than likely going to be ionic in nature. Which brings me to this fun chart here. And this is more of a mathematical representation of bond type. So you can calculate what that bond is going to be like if you subtract the electronegativity values of two different elements. So in sodium chloride's case, if we take their electronegativity values, chlorine has an electronegativity value of 3.0 and sodium has an electronegativity value of 0.9. So if we subtract those, we get 2.1. And since 2.1 is above this line of 1.8 right here, that means that that bond is going to be ionic in nature. Comparing that with this here, this CO bond, carbon has an electronegativity value of 3.5 versus oxygen of 2.5. So that's going to be a 1.0 difference, okay? And that falls between this line here and this line here, meaning it's a polar covalent bond in nature. And then if you move over here and you're looking at the bond in between carbon and hydrogen, carbon having 2.5 electronegativity and hydrogen having 2.1, in that case, we get a 0.4 difference, which falls under a non-polar covalent bond. Now, what I want to say about that is it's not perfectly non-polar, right? There's still a little bit of a difference here. So those electrons are probably going to hang out with carbon a little bit more, but it's close enough that they can kind of move more freely back and forth. A true non-covalent, or sorry, not non-covalent, non-polar covalent bond would be between atoms of the same type. So a fluorine to fluorine bond would be an example of a true non-polar covalent, or chlorine to chlorine, or something like that. So talking about bond polarity and dipole moments, any diatomic molecule that has a polar bond will show a molecular dipole moment. So that's really just that notation again with the arrow. So between H and Cl, that would be their dipole moment because that molecule is polar due to that difference in electronegativity, right? So to really be able to label things like this effectively, you have to consider the molecular geometry of the molecule that you're at. So looking at water, a lot of people in general chemistry, they draw water like this, right? And that looks like water is linear, and it's really not, because what these electron pairs are going to do is they're actually going to bend water into a more bent shape. And so what water actually looks like molecularly is something like this, right? So comparing those two forms to one another, what this is telling you, this being the more inaccurate one over here, it looks like water is linear, and we're seeing less in electronegativity on both sides. So what this molecule looks like is it looks like it wouldn't be a polar molecule because you're seeing no dots on the left, no dots on the right. So there's not a huge difference across the molecule. And it looks like these electrons next to oxygen are kind of hidden in the middle. So maybe you might see it up there and down here. But again, this isn't super accurate. But if you factor in the geometry and what these electron pairs are forcing the molecule to do, suddenly you have a huge electronegativity difference between ends of this molecule, right? All your electrons are hanging out with oxygen and not with those hydrogens. So you get a visible dipole moment in that molecule. I'm sorry, I drew that arrow incredibly backwards. My apologies. Let me just fix that. There we go. So again, huge dipole moment in that water molecule where it's not super obvious if you don't draw it with the right shape. So we will get to molecular geometry in a little bit, not currently right now, but we'll start factoring that in as we go. But the thing is that some molecules, they have polar bonds, but they don't actually have a dipole moment. And that has to do with the shape of them a lot of times as well. So if you look at this table, linear molecules with two identical bonds would be an example of something that has polar bonds, but no overall dipole moment, because this is what carbon dioxide looks like drawn out. That's a linear molecule, right? And we know that those bonds are polar, but the molecule itself is not, because you have these partial negatives at either end, and the positive portion of it would be in the middle. Okay, so Another example would be planar molecules with 3 identical bonds that are about 120 degrees apart. And this is a good example of what I'm talking about there, this SO3, because again, what you're seeing is you're seeing O's, 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 and the S's in the middle. So you're not really seeing a difference across the entire molecule. Or CCl4 or even CH4, if we superimpose those where they're supposed to go, right? Because all of those become like that. And then there's no dipole moment over the entire molecule, even if those bonds are in fact polar. All right. So next, just to briefly touch on energy effects in binary compounds, when a molecule bonds together, right, there's an energy change that's taking place. We talked about this in regular chemistry a little bit. When gaseous ions are packed together, forming an ionic solid, we call that energy change delta H lattice, or lattice energy, right? And lattice referring to the structure that the ionic solid forms, okay? So if we are talking about metal with nonmetal forming a crystalline structure, there is an energy change that takes place when that solid is formed, or an equivalent energy change if that molecule were to break back apart, but that energy would be going in the opposite direction, right? So lattice energy can be defined as the energy released when an ionic solid forms, or the energy absorbed when an ionic solid separates into its ion. And depending on what is happening, that delta H could be negative or it could be positive. So again, you're seeing that negative sign or positive sign reflecting what direction the energy is going. Real quick, here's an interesting example that I'm going to show you about the heat of formation of lithium fluoride. So what actually happens when this compound forms is there's a lot of different steps that take place and a lot of different reactions actually. And each one of them has a different energy associated with it. So if that lithium is going from a solid to a gas, that is going to require 161 kilojoules of energy to take place. If it's going from its gaseous state but ionizing, that's going to require 520 kilojoules to do. If this half reaction, which again, I'm not going to spend a lot of time on explaining why that happens, we'll get there later, but if that takes place, this half fluorine molecule and then splitting up, that's going to require 79.5 kilojoules of energy to take place. If fluorine's ionizing, that actually releases some energy, and that's what that negative sign means. Lithium and fluorine bonding together releases some energy, hence the negative sign here. And so overall, this is your total reaction that's happening once we kind of add all of these things together. And overall, there is a release of energy there that is happening. But that process takes some energy and releases some energy. So this is what we call a net energy at the very end. And that's related to Hess's law, which again, we'll talk about a lot more later, but not currently right now. Lewis structures is next on the agenda of things to talk about. So you have had an introduction to this before. You've drawn Lewis structures before in chemistry, and so this is basically going to build on that. So to remind everyone of the octet and the duet rule, the octet rule basically says that atoms want to have a full outer valence shell. And usually that full outer valence shell contains 8 electrons normally. But with hydrogen and helium specifically, they only have 2 electrons in their outer shell because if you recall, they just have that one S subshell to fill. So when you determine Lewis structures, there's a ton of ways you can do this, you guys. So this is the official way. Determining the number of electrons needed to satisfy that octet duet rule, subtracting the total number of valence electrons from that number, then dividing that answer by 2, and that'll tell you how many bonds you have to draw. Personally, I don't favor this method, though it works. So if you would like to use that method, I will not stop you, but I favor a slightly different method, and I'll show you what I mean. So with NH3, we have 4 total atoms there. We have 1 nitrogen and 3 hydrogens. So what I like to do is I like to total my number of valence electrons first. So if we look at the periodic table, we know that nitrogen has 5 valence electrons, and there's only 1 nitrogen in this molecule, so I'm going to leave that number alone. I'm going to add 3 times hydrogen's valence electrons, and we know hydrogen has 1 valence electron because of its group on the periodic table, and since there are 3 of them, I'm going to multiply that by 3. So when I add all that together, I end up with 8 valence electrons. Now I did this first because what this tells me is that I need 8 valence electrons accounted for when I draw my structure out. So that helps me personally more than knowing how many bonds I have to draw. And the reason that that helps me more is because when certain things are ions, when you have polyatomic ions, this number means more than the amount of bonds that you should have. To me, again, this method up here is completely workable, but I favor my method. So I'm going to show you that. Okay. Now, for drawing Lewis structures, you're going to put an atom in the center, the least electronegative, never hydrogen though. If carbon's present, it's always going to go in the center. You're going to arrange the rest of your atoms in a symmetrical pattern surrounding that, and you're going to connect everything with a bond line. Any leftover electrons, you have to move around in place to satisfy octet rules if you can. And the number of electrons in your diagram must equal the number of valence electrons. So the way you draw it, counting your electrons makes more sense to me. So moving on to my examples here, and keeping in mind that we already told ourselves that we need to account for 8 valence electrons for this NH3 molecule, we're going to practice drawing it. So step 1 told me to place my central atom. So that's going to be our nitrogen. And you know that because there's only 1 nitrogen and hydrogen can only bond 1 time. And so it doesn't make any sense for hydrogen to be in the middle. Then we are going to place our hydrogens somewhat symmetrically around, and we're going to connect everything with a bond line. All right. So now that we've done this, we need to check and see if we have accounted for all of our valence electrons. I'm going to switch colors. Each bond accounts for 2 electrons being shared. So if we count our 3 bonds and multiply by 2, we get 6 valence electrons that we've accounted for so far. We need to account for 8 total, which means that there's a pair of electrons somewhere or potentially another bond. But hydrogen, we know, since it only has 1 valence electron, can only bond 1 time. So it can't be another bond. So there has to be a lone pair. And that lone pair is going to get placed on nitrogen because nitrogen is the more electronegative between hydrogen and nitrogen, right? And it's also the central. So that lone pair is going to exist on nitrogen. And if you remember from last year, we know that nitrogen has 5 valence electrons anyway. So if we just count, nitrogen should have those 5. Okay. So moving on to HCN. This one contains a carbon, so automatically we're going to put the carbon in the middle and we're going to put the nitrogen on one side and the hydrogen on the other. And we're going to connect those 2 with bond lines. Okay, so automatically we can do that without even knowing our total amount of valence electrons. But we may not know how many bonds we need or if there's any lone pairs. So looking at our molecule, hydrogen has 1 valence electron, carbon has 4 valence electrons, nitrogen has 5 valence electrons. So we get a total of 10. So far, we have accounted for 4 of them in our molecule because we've drawn 2 bonds. So hydrogen can only bond 1 time, so we probably aren't going to end up adding another bond on that side, but carbon can bond 2 more times. And nitrogen can also bond 2 more times based on its amount of valence electrons. So we can draw 2 other bonds there and try to account for all of those electrons. But we're going to check one more time, 2, 4, 6, 8. So we've accounted for 8, not 10, leaving us with 2 remaining, which again, there's going to be this lone pair circulating around nitrogen because it showed up here, it's showing up again there. And this molecule is neutral, so we don't have to worry about a charge taking place anywhere. Last but not least, we have this N2O minus, okay? So now we have something with a charge. So when we're figuring out our amount of valence electrons, we have to make sure we account for that extra electron represented by the negative charge. So we have 2 nitrogens. Nitrogen each is going to have 5 valence electrons plus oxygen, which has 6 plus an extra 1. So that's going to give us 17 total. So when we draw this, we're going to put our oxygen in the center potentially because there's only one of those. So it would make the most sense. We're going to put our 2 nitrogens on either side and we'll see if that works out. So the first thing we're going to do is we're going to connect some stuff with the bond line, right? We know that oxygen has 2 lone pairs normally. So I'm going to go ahead and add those in. And I know that nitrogen usually has at least 1 lone pair per. So what we're seeing here is that neither nitrogen's octet is currently satisfied, but oxygen can only bond twice if it is to be neutral, right? So we're seeing that this structure may not work necessarily. And we could try to add more bonds. We could try that to try and satisfy nitrogen's octet rule. But then what's happening if that takes place is there ends up being a positive charge on this oxygen, which does not match the negative charge that we are supposed to have. So that's actually not a good structure for N2O. And the reason that it's not a good structure is because we didn't follow the very first rule in how you're supposed to place your central atom. Generally speaking, you want your least electronegative in the center, and oxygen is actually our more electronegative. So even though there's only 1 oxygen and it seems like it would make sense for it to go in the center, it doesn't. So let's try again. Let's try placing one of our nitrogens in the center instead and put another nitrogen on the side and one of the oxygens on the side, okay? So now we're going to try to do the same thing with the valence electrons. We know that oxygen generally is going to have 2 lone pairs. We know that each nitrogen is generally going to have at least 1 lone pair on it, okay? So now what we're seeing is an opportunity for more bonds to be placed potentially. So we know that nitrogen can bond up to 3 times. So we can go ahead and place another bond here. And what that means is that this nitrogen in the middle, that its octet is full now, right? It has 1, 2, 3 bonds coming off of it. It's 2 lone pairs. This oxygen, however, is not actually satisfied yet, and neither is this nitrogen on the other end. So what I'm going to do first, before I do anything else, is I'm going to check and see how many electrons I've accounted for. So I have how many bonds? I have 3 bonds total. So 2, 4, 6, 8, 10, 12, 14. So I need to place somehow, some way, 3 more electrons, which is weird. So let's see what we can do here. We could theoretically draw another bond here. So if we do that, if we draw another bond, then this lone pair gets roped into that bond, right? So this lone pair kind of goes away, right? And we have just, I'm going to put an extra electron because one of those electrons is going to get roped into this lone pair. And we're going to pretend that this one is just floating over here for a second. Please do not forget that it exists. what also happens if you don't draw another bond over here is those extra electrons we have to place have to go somewhere. So they're going to hang out next to the least electronegative atom, or not least, the most electronegative atom possible. So those might hang out around oxygen. Okay. So now we have some octets being satisfied and some extra electrons hanging around. So we have an extra electron here and we have a lone pair here. Okay. So if you recall that a bond is a share between two electrons, but there's still a lone pair over here. What happened with that extra electron that seemingly went away? This lone pair that we just disappeared over here, that actually moved and formed a bond. Okay, so this lone pair is still there, and this is not a lone pair anymore. It's now part of a bond. So our final structure is going to look like this. So now what we're seeing is a charge that matches our original charge in our molecule. And we're seeing a structure that is indeed possible. Okay. So what I want you to think about when I'm drawing this is not worrying so much about how, oh my God, that didn't make any sense to me. Because again, we're going to go over resonance and we're going to go over how electrons move around. And some of the ions are very hard to draw in Lewis structures. Okay. So keep that in mind. Keep in mind that electrons can hop around, and we'll go on to resonance. Resonance structures exist because electrons can move. All right. So in O3, which is our example down here, we're seeing delocalized charges happening. And that happens again because of the movement of electrons. So basically, what we're seeing to get from this structure on the left to this structure on the right is this double bond is hopping around. What actually happens there is that the electrons that are shared by this bond, those two, are going to hop over here to this oxygen. And then this electron pair that's right here is going to hop down and become a new double bond. That is what is happening. So when that happens, you end up with this, right? So you end up with something like this, okay? Now, what happened here? We have our two lone pairs on that. We still have a lone pair here because this bond over here became a new lone pair. This lone pair originally that was on top hopped down and became a double bond. And we still have this happening. So that doesn't look exactly like this molecule over here, right? Because our lone pairs don't match. But when you have a double bond here in this situation, an extra lone pair on oxygen isn't very stable of a setup. So that lone pair is actually going to migrate back through our molecule and end up over here on this one instead. So that's going to move around, and it does that in a few different ways, which I'm not going to talk about a whole lot right now. But at the end of all of that movement, you get your second resonance structure. But another way we could have represented this molecule, instead of movement and a bunch of different structures, we could have also said this and drawn it with a dotted line instead. And what that signifies is that that double bond can actually move around, okay? That double bond can move. So if you see a dotted line like that, that's what that means. Okay, last but not least, we are going to calculate some formal charges here. And I apologize that this example does not match the picture, but it's actually not N2O, but NO2 that we're going to do as our example. So when we calculate formal charge, we have to determine the number of valence electrons in our atom and subtract 1 for each bond line, and then 1 for each dot. So with this leftmost oxygen over here, we know that oxygen, based on its group on the periodic table, has 6 valence electrons. We are going to subtract 1 for each bond line that's attached to it. So you can see this one single bond coming off of it. We're going to subtract 1 for each dot. So we have 2, 4, 6 dots over here. So overall, our formal charge on that is going to be a -1, which matches what we see in the diagram. This nitrogen here, nitrogen has 5 valence electrons. We're going to subtract 1 for each bond line. So there's 3 bonds coming off of nitrogen. So we're going to subtract 3. And then we're going to subtract 1 for each dot. There's 2 dots there. So that's going to be a 2. 5 minus 3 minus 2 gives us an overall formal charge of 0. As for our last oxygen over there, again, oxygen has 6 valence electrons. We're going to subtract 1 for each bond line, which in this case is 2, and 1 for each dot. And then we see 4 dots around that oxygen, which gives us an overall formal charge of 0, which again matches what we're seeing in the diagram. We are going to use formal charge basically as a guess and check if we're drawing our structures correctly. And also we will use it later when we figure out oxidation numbers as well. All right, so this sample problem, drawing out the Lewis structures for NCO- and calculating the formal charge of each ion. We did this in class, so I'll go over it really quickly. Carbon is going to go in the center, and then oxygen and nitrogen are going to go around the outside. Just to double check and how many valence electrons we need to account for, we have 5 for nitrogen plus 4 for carbon plus 6 for oxygen plus 1 more for that extra electron that's there. So we end up with a total of 16. Now drawing our bonds, we know that carbon can bond 4 times total. So we have choices. A lot of people are tempted to draw 2 double bonds between each, but that's not actually going to be the most stable form. We're actually going to end up with a triple bond between carbon and nitrogen and a single bond between carbon and oxygen. And we have to draw in our lone pairs as we know that each element has. As a double check to see if we have accounted for all of our electrons, we need 16. We have 2, 4, 6, 8, 10, 12, 14, and we need to place 2 more. Oxygen's octet is not satisfied yet, so we're going to draw in our extra pair right on oxygen because oxygen is the most electronegative, and therefore that negative charge is going to go right there around oxygen, and that is going to match our charge of our original molecule. All of our electrons are accounted for, and we can calculate our formal charges. Nitrogen has 5 valence electrons. Subtracting 1 for each bond line coming off of it gives us -3. Subtracting 1 for each dot gives us -2. And that's going to give us an overall formal charge of 0. Carbon comes next. We start with 4 for carbon, subtracting 1 for each bond line coming off of it, which in this case is 4. And then there's no dots surrounding carbon, so we're going to get a formal charge of 0. That last oxygen has 6 to start with. We're subtracting 1 for each bond line coming off of it and 1 for each dot, which gives us an overall charge of -1. Moving on, last but not least, I want to talk about exceptions to the octet rule. Certain atoms are what we call electron deficient, and they bond with fewer than 8 valence electrons. Examples of that would be beryllium, boron, or aluminum. Odd electron molecules have odd numbers of valence electrons. Those are known as free radicals. They are incredibly unstable. This would be an example, this NO molecule, but we're seeing that extra random electron just hanging out. That makes it a free radical and an unstable molecule. And then this one is going to be the one that's the most important to you, expanded valence shells. So some shells are going to expand to accommodate more than 8 valence electrons, and that's going to require a D sublevel in most cases. And so the most common examples of this are sulfur, phosphorus, and silicon. Some elements can do it in a few different ways, not always with the D shell, but these are the examples I would like you to know about. On a test, if there's another example there, I would call that out for you. So that concludes our notes for today. If you have any questions, please see me in ELT.